You know, the universe, it's a pretty violent place. We're talking about supernova explosions, matter swirling into black holes, gigantic clouds of gas way hotter than the core of our sun. These are like cosmic crime scenes. But the thing is, they're happening millions of light years away, and a lot of the time, they're completely invisible to our eyes. So, how do we investigate? How do we possibly figure out what happened?
Okay, so let's get into it. The secret is that these insane events, they always leave behind clues. They can't just hide from the laws of physics, right? But to find those clues, we have to look at the universe in a completely different kind of light. A type of light our eyes can't see, but our telescopes, oh yeah, they definitely can.
That's right, X-rays. The very same kind of energy a doctor might use to see the bones inside your body, well, the cosmos uses it to broadcast all the juicy details of its most powerful moments. These X-ray signals are basically secret messages, and if we can learn to decode them, we can solve some of the universe's greatest mysteries.
To do that, just like a detective, we need a gallery of suspects. In X-ray astronomy, we think of the specific signal, or the spectrum, from a cosmic event as its own unique fingerprint. And just like real fingerprints, no two are exactly alike. So our job as cosmic detectives is to learn how to read these prints.
So the X-rays that get blasted out by these cosmic events, they tend to leave behind three main types of fingerprints. As you're about to see, they kind of look like a sharp curve, a straight line, or a broad hump. Each one tells a totally different story about how those X-rays were made. So let's open the case file on our first suspect. So our first fingerprint comes from places of just unbelievable heat. I mean, think about these massive clouds of gas floating between galaxies, or the debris that's left over after a star explodes. We're talking about gas that's been heated to over 10 million degrees Kelvin. That is hotter than the very center of our sun.
And the process that makes these X-rays has this fantastic German name, bremsstrahlung. It literally means breaking radiation. And that's exactly what it is. Imagine, in this superheated gas, you've got these tiny little electrons just zipping around at insane speeds. When they fly past a heavier atom, an ion, its gravity gives them a little tug, and it bends their path. It's like they're slamming on the brakes. And that sudden change in direction, that loss of energy, gets shot out as an X-ray.
So the fingerprint this whole process leaves behind is this broad, continuous curve. The peak of that curve, right there, that's the key. Its position tells us the exact temperature of the gas. See, hotter gas means faster electrons, which make higher energy X-rays, so the whole curve shifts. Just by looking at the shape, we can take the temperature of a gas cloud millions of light years away. It's amazing.
But hold on, our detective story is about to get another layer deeper. This broad glow isn't the only clue hiding in that gas. There's something else hiding right there in plain sight. See those sharp spikes sitting on top of that smooth curve? We call those emission lines. In that same hot gas, you've got atoms like oxygen and iron that are just getting supercharged by all that heat. When their electrons fall back down to a lower energy state, they spit out an X-ray with a very, very specific energy. And each element has its own unique set of spikes. It's literally a chemical barcode. By reading these lines, we can tell you exactly what that cosmic crime scene is made of.
Okay, time for our next suspect. This fingerprint isn't made by heat at all. It's a combo of incredible speed and ridiculously powerful magnetism. We're talking about nature's very own particle accelerators.
This is called synchrotron radiation, and for this you need two key ingredients. First, you need electrons moving at almost the speed of light. We call that relativistic speed. Second, you need powerful magnetic fields. So when one of these super-fast electrons flies into a magnetic field, the field just grabs it and forces it to spiral around. This constant whipping around corners forces the electron to shed energy as radiation, and when the conditions are just right, that radiation pops out as X-rays.
Now, the fingerprint from this synchrotron radiation looks totally different from what we saw with the hot gas. I mean, just look. Instead of that curve, it gives us a spectrum that looks like a straight line on our charts. We call this a power law spectrum, and for an astronomer, it is a dead giveaway. When we see this signature, we know we're not looking at a hot cloud. We've found a powerful cosmic accelerator.
And where do we find these incredible accelerators? Well, they're in some of the most extreme places in the entire cosmos. The expanding shock waves from exploded stars, supernova remnants, they're famous for this. And even more powerful are those colossal jets of particles that get shot out from around supermassive black holes at the centers of galaxies. This straight-line fingerprint is their calling card.
All right, let's move on to our third and final main fingerprint. This one is maybe the simplest of them all.
It's not from some spread out gas or a crazy accelerator. It's from a solid, dense object that is just plain hot. This is what we call black body radiation. It's the kind of light you get from any dense object simply because of its temperature. Now here's the crucial part. For a perfect black body, the kind of light it gives off depends only on its temperature. A fantastic cosmic example is a neutron star, that incredibly dense core that gets left behind after a big star explodes. If it's hot enough, its surface will just, well, it'll glow in X-rays.
Honestly, the best way to think about this is a classic electric stove element. You turn it on low, and it starts to glow that dull red. You crank up the temperature, it gets brighter, turns orange, then yellow-white. What you're seeing is the peak of its blackbody curve moving to higher and higher energies. A neutron star is just so mind-bogglingly hot that the peak of its glow isn't in red or white light. It's way, way up in the X-ray part of the spectrum. The shape of this curve tells us its surface temperature. Plain and simple.
Now I have to share one bonus clue. It's too cool to skip. Sometimes X-rays aren't created from scratch. They get upgraded. Imagine a low-energy photon, just a bit of leftover light from the Big Bang, just kind of wandering through space. Then bam, it gets rear-ended by one of those relativistic electrons we were just talking about. In that collision, the electron transfers a huge chunk of its energy to that little photon, and it instantly transforms it into a powerful X-ray. This wild process is called inverse Compton scattering, and it's just another trick the universe has up its sleeve.
Our solar system is constantly invisibly glowing. It's this constant barrage of energetic particles and X-rays hitting pretty much everything out there. Mostly, we're talking about charged particles shooting out from our sun and various planetary magnetospheres.
But you know, it's not just particles. There's another kind of projectile in the mix.
Yep, X-rays straight from the sun are also zapping cold objects all over the solar system.
Basically, everything's a target. We're talking planets, their moons, and even comets get in on it.
And boom, the target actually glows with X-rays.
But are all these X-ray glows the same? Nope, it all depends on what did the hitting. When those particles strike, two kinds of X-rays pop out.
They're called bremsstrahlung and fluorescent X-rays.
And those fluorescent X-rays? Well, they're super important. Think of them like a fingerprint.
Right, because their energy tells us exactly what the target is made of and what hit it.
What happens when solar X-rays are the ones doing the hitting? This time you get scattered X-rays, kind of like reflections, and, you guessed it, more fluorescent X-rays.
So what does this all mean? Our solar system is literally glowing with invisible light all the time.
So there we have it. We've got our gallery of fingerprints, the broad curve of hot gas, the straight line of a cosmic accelerator, and that simple glow from a hot surface. Now we can finally solve the case.
And this is why this all matters so much. When our X-ray telescopes, amazing machines like Chandra or XMM Newton, detect a new source out there in the sky, we collect its light and we draw its spectrum. Is it a broad curve with those sharp emission lines? Okay, then it's a cloud of hot gas, and we can measure its temperature and tell you what it's made of. Is it a straight power law? Bam! We've found a cosmic particle accelerator. It is literally forensic science on a cosmic scale.
But, you know, no good detective story is complete with one final twist. These X-ray messages have to travel for millions, sometimes billions of years to reach us. And space? Well, it isn't completely empty. So what happens when the clue gets contaminated on its journey?
Well, as these X-rays travel through all the thin gas and dust that drifts between the stars, some of them get absorbed. And it turns out, lower energy X-rays get blocked way more easily than high energy ones. This whole process acts like a filter, and it basically chops off the left side of our spectral graph. It smudges the fingerprint before it ever gets to our telescope.
So, the final step for any real cosmic detective is to carefully model and correct for this absorption. We have to digitally wipe away that smudge to figure out what the fingerprint looked like the moment it left the source. Only then can we make a positive identification and be sure we've actually solved the mystery of what's going on out there in the dark.
Translating the secret language of X-rays into these amazing stories of heat and speed and magnetism. But as our technology gets better and our telescopes get more powerful, we are bound to find new, even more exotic fingerprints that we've never seen before.